Hi, this video brings us to the end of our little introduction to trigonometry. In this introduction, we have looked at angles, and we will conclude by looking at how we can use this knowledge to find the length of an arc and the area of a sector. So this is the arc of a circle, and this is a sector here. We know that in radians, an angle is defined as the ratio of the corresponding arc, the length of this arc, to the length of the radius. And that's given by this expression here. So given this expression here, we can transform it, and given the radius of the circle and the angle in radians, we can then easily find the length of this arc. So here are some examples of that we can work with. These problems are fairly trivial. They involve only substituting into this formula. I urge you to make sure you understand where these formulas are coming from. Make sure you always understand just what it is these shortcuts cut short. So in this first case, we have that the radius is 23 and we need to multiply it by the angle in radians. We just ask ourselves, well, 25 degrees, what fraction of 180 is that? And whatever that is, well, that's going to be how much of pi this angle is in radians. So 25 over 180 times pi gives us 0.436, and then of course we get 10. So the length of this arc is 10. Now, you don't necessarily have to use this formula. This is why I'm always stressing that you understand what's going on. You can simply say that the length of half a circumference is simply pi times r, pi times 23. And then what fraction of this half a circumference do you want? Well, it's the ratio of 25 to 180. So you just say 25 out of 180. That's going to be the fraction of this half a circumference that you want. And of course, half the circumference is pi times 23. Remember, for the full circumference is 2 pi r, so pi times r is half the circumference. So if you were to forget this formula, and I don't see why you would forget it, but if you were to forget it, you can still figure it out. It's just how much of 180 is this angle, and then that's going to be the fraction that the corresponding arc is of half a circumference. So think about it for a while and try and see that it makes sense. So the rest we'll just substitute into the formula. In this case, it's 17 times the angle in radians, so that's 140 out of 180. So it's still less than half a rotation, and times pi, and we get this. And then it's 65 in this case times the angle in radians, which is 240 over 180. So now it's more than half a rotation, but not yet a complete rotation, and we get 4.328 radians. So 65 times this gives us this as the length of the arc. Always remember this definition here, right? It's just simply the angle is defined as a ratio of this arc to the radius. The bigger the angle is for a given radius, the bigger is going to be the length of the arc, and there's a proportionality between the two of them. For this last one here, again, 300 over 180, it's more than half a revolution, but not quite a full revolution yet. And so that's going to be 31 times 300 over 180 times pi. Alright, so let's look at how we can find the area of a sector then. A sector of a circle is a region that is bounded by two radii of that circle and the intercepted arc. So here we have a sector. Note you could also call this a sector, but for now let's focus on this little one. The argument that we'll make still holds no matter what. So now, what's the area of this sector? Well, to find the area of the sector, all we need to know is the ratio between this rotation here, represented by this angle, and a complete rotation. The ratio of this angle to a complete rotation is going to be equal to the fraction of the complete area that the area of the sector represents. So finding the area of a sector is simple. All you need to do is find the ratio of the angle to a complete rotation. Note that this can be in degrees, in which case this would have to be 360, or in radians if you make this 2 pi. And you find that ratio and multiply it by pi r squared. So let's say, for example, that we're dealing with a quarter of a rotation. Then that would be 90 over 360, which gives us a quarter, or pi over 2 over 2 pi, which also gives us a quarter. In both cases, if it's a quarter of a rotation, the area would be a quarter of the complete area of a circle, which is pi r squared. In other words, it would be 1/4 of pi r squared. Now this equation can be simplified. Notice we have pi here and pi here. If we carry out the simplification, however, notice now we don't have this ratio anymore. And so if we're going to use this equation, this angle has to be in radians. You cannot use this angle in degrees. If you're given degrees, you need to convert it to radians. So let's look at a few examples now. We are here asked to find the area of sectors given the angle and the radius. So let's look at this first one here. We'll simply use the formulas placed here. Again, I'm a bit wary of using formulas just like that. It's very easy to be led astray with this, and it doesn't really involve a lot of thinking. There is no critical thinking involved in simply substituting values into a formula. So just be aware of this, right? It's more important that you understand where this formula comes from. What process is it encapsulating? And really what it's doing, it's the result of comparing the angle to a complete revolution and then the area of the sector to the area of a complete circle. So remember that. Anyway, having said that, let's just plug these values. So this is called plugging and chugging. We have the angle 15 degrees. Remember, we need to have this in radians, so 15 degrees is how much of 180, and then we multiply it by pi. That gives us the angle, and then we multiply it by the square of the radius, and we get 22.12. If you forget this formula, you should still be able to solve this problem, because all you need to know is that, well, the corresponding sector has an area that is what fraction of the total area? Well, the ratio of 15 to 360. Notice that these formulas, if you rearrange them, you get the same thing. This 15 over 360, I could write 180 here, and then it becomes 1 over 2 times 15 over 360. And then this pi, I can write it up here, and then 13 squared. So these formulas are identical. Only that here you can't really see the thought processes involved, while here you can. So I'm not against formulas. Formulas are good, especially if you are writing programs. For example, when I do online quizzes, the computer can't think, so I have to give it a formula. So in a sense, formulas become important when you want something that can't think to solve a problem. So I'm not saying don't use formulas, but just you need to have a good understanding of these formulas. In this case, again, we're just plugging and chugging. We have 130 degrees. Well, to convert this to radians, that's what we do here, and we get our answer. In this case, by the way, if I'm going too fast, you can simply pause the video and crunch these numbers yourself. So here it's a half times the angle in radians times 25 squared. And here it's a half times the angle in radians. Notice it's the ratio of 330 to 180. And then we multiply it by pi. Remember, 180 corresponds with pi. Anyway, see the answer here. And so that brings us to the end of this video. In the next video, we'll start looking at what is more traditionally known as trigonometry. We start looking at sine and cosine and tangent. Okay, so until then, bye.